Hello. So in this video, we're going to focus on solving some problems related to phase equilibrium. Specifically, in this case, we're going to talk about problem-solving strategies for vapor-liquid equilibrium using the example of a flash evaporator. So a flash evaporator is a simple separation unit. So basically, it's a tank. So you flow some stream of liquid into a big tank, and the tank is held at some temperature. The mixture is allowed to equilibrate, and out of the top of the tank comes a vapor that's in equilibrium with the liquid. So this is run in a continuous process. So you have a flow of material in, and it happens pretty slowly. So you slowly extract material out through the vapor and liquid streams. So this is sort of a very simple separation unit that that's a step towards something like a distillation column that uses different multiple stages of doing this to get more high purity products. So we're going to assume everything is at equilibrium to solve these types of problems. So let's get into this. Okay, so here is my diagram uh, of a flash evaporator. So we have one stream coming in. We're calling that F. That's our feed stream, and we have two streams coming out. We're calling them V for the vapor stream that's coming out the top, and L is a liquid stream coming out of the bottom. I drew this full of fluid, and we're going to use these variables, V, F, and L, as the flow rates of the respective streams. So those will be some molar flow rates. So let's say that there are two species in this flash evaporator. I will call them 1 and 2. So we can say that the feed stream has a concentration or mole fraction of species 1 called Z1, and a mole fraction of species 2 we'll call Z2. Likewise, for the vapor stream, we'll use the variable y, y1 and y2. And for the liquid stream, we'll use x1 and x2. We can do a material balance in the system. So overall, we can say that the flow rate in equals the flow rate out. So the feed stream equals the feed stream flow rate equals the sum of the vapor and liquid stream flow rates. We can also do a species balance. So we can say that for either component 1 or 2, we can say, for instance, Z1 times the feed stream, which would represent the flow of species 1 in the feed stream into the flash evaporator, equals YIV plus XIL. So this essentially just means that species I going in equals species I going out through the two streams. So in addition to material balance, we also have some equilibrium criteria that we can talk about. As always, when we're talking about phase equilibria, we can say that the chemical potential of any given species I is the same in both phases. In this case, vapor and liquid, that we're denoting using V and L respectively. As we've learned in the last week, we use fugacity in solution, this F, with a caret over it, as a proxy for chemical equilibrium or chemical potential. So we can say the fugacity in solution of any species in the vapor equals the fugacity in solution of that species in the liquid phase. So in many cases, this will simplify to this equation, YIP equals XI gamma I times the saturation pressure of species I, where gamma I is the activity coefficient. you may remember that this equation we have here is what we call modified Raoult's law, which assumes that we have a non-ideal solution. The activity coefficient can be a function of a bunch of different things depending on the model that you use. For instance, it typically will be a function of temperature, could be a function of pressure, and it is a function of xj not equal to I, meaning if you're considering the activity coefficient of species I, the concentration of components that are not species I will be it'll be a function of. The saturation pressure is a function of temperature, and we've been using the Antoine expression for that. And recall that for an ideal solution, the activity coefficient is 1. And this will reduce to Raoult's law. So again, just to recap, we have a material balance, which basically tells us the flow in equals flow out, either of the total number of moles going in, the total flow rate, or of any given species. And we have an equilibrium condition that is given by modified Raoult's law, or yp equals xi gamma I pi sat, or in this case, species 1. I've written this all. So remember, for another thing that we need to remember is Gibbs phase rule. So this is written as F equals 2 plus n minus pi, where n is the number of species. In this case, example, we have 2 different species, and pi are the 2 phases. We have, in this case, 2 liquid and vapor. So F is the number of degrees of freedom in our system, which is 2. So this means that we need 2 independent variables defined to completely determine the system. So what independent variables do we have? So in our system, for any system, we will have the temperature and pressure, which could be defined, and n minus 1 mole fractions in each phase. So we have n minus 1 because if we define all the mole fractions except 1, the other one will just be 1 minus the other one. So the number of independent mole fractions will always be 1 less than the total number of species that we have in our system. And that's in each phase. So in our system, we have 2. This should be 2 because the number of phases we have is 2 and the number of species we have is 2. If you work this out, that means that the number of independent variables in our system is 2. So what does that mean? Right? So we can write out all of our variables in here. And in their case, of the flow system, we also have these flow rates. So in terms of the intensive variables, meaning the things that are in the system itself, if we define pressure and temperature, we can define x and y. If we define x and t, we can figure out what p and y are. If we define what x and y, in some cases we can figure out that the pressure and temperature that occurs, but what you'll find is that that is only the case if a condition exists. So if you could define an x and y that isn't possible. For example, in the most extreme example, you could imagine if you're distilling, separating water and ethanol, you could claim that you have some equilibrium vapor above some very dilute um, alcohol that is pure species one. Of course, we know that can't happen. So we won't. What we'll find if you try to define x1 and y1 in a way that doesn't make that can't happen, you won't be able to solve it. The other thing that can happen is you can also have more than one solution, depending on the you may find that there are multiple pressure temperature combinations that will give you a particular XY combination that you choose. So typically, you for practical purposes, there isn't really a reason to define both X and Y. Typically, you want to understand at a given pressure and feed composition, for example, what would you be getting out of a particular stream. Okay, so this tells us what can be specified, and you should note that this what we're talking about here assumes that no chemical reactions occur, and we'll deal with how to handle that later. Okay, so that's all we have for right now. You should feel free to contact me if you have any questions about this. Read through the section of the textbook, and we'll work through an example related to phase equilibria soon in a following video. See you next time. Bye.